Let's look at the Nusselt number for the entry region. So the Nusselt number for the laminar flow that we saw, 3.66 for constant TS and Nusselt number 4.36 for constant surface flux. These two are valid when both temperature and velocity profile, temperature and velocity profile are fully developed. However, there are cases that both of them or one of them at least is not developed. If the profiles, the velocity and temperature, if you are in the entry region, both velocity and temperature, like velocity is going to be function of x and r, and temperature gradient is also going to be function of x. And then the Nusselt number, that's going to affect the heat transfer that's happening from the system. Now, generally, like the way that we deal with that, we plot a plot of, I would say, local Nusselt number as a function of dimensionless parameters called Gratis number or Gratz number. As a function of Gratz number, inverse of that is something like that. So if I plot local Nusselt number D as a function of Gratz number to the power of -1, just gonna call it Gratz number, and the way that we define this dimensionless parameter, Gratz number D is D over X Reynolds Prandtl. So -1 is gonna be X over D X over D. Let's write it in this way. Prandtl Reynolds. That's going to be inverse of Gratz number. Now, for the constant surface temperature, what we are going to see here is change here that reached to the point 3.66. So it's reached to this converging to the fully developed for the Nusselt number for a fully developed laminar flow, and for the constant flux, it's going to be similarly going down and reaching to 4.36. So this is for the constant surface heat flux. So that's going to be the change of the local number, Nusselt number, and this is going to be for the constant surface temperature. And if I want to put number, this is in the log scale, so it's going to be like around 2, 4, yeah, around 8, 10, and at the end we're going to have around like 20. And the lengths that you are going to have the change from the developing region. So this is the entrance region. And this is the fully developed region. That's going to be around 0.05. So at the fully developed region, both of the Nusselt number for both constant flux and constant temperatures, they are reaching to the constant value of 4.36 and 3.66 when we have, so for the fully developed region, the fully developed region reaches at this number v over x Reynolds number parental almost 0.05. Both of them are reaching to that point. And for the constant temperature, we have a correlation for the constant surface temperature, Ts constant. What we have, the average Nusselt number is going to be 3.66 plus 0.08, 668. That's number 1 plus 0.04. That's number d to the power of 2 over 3. And these correlations is with the assumption, it assumes that flow is dynamically developed. So that's the assumptions, or develop when fluid enters the heating section. That's the assumption behind that. However, if we have a Prandtl number greater than 5, we can use the above equation. It is applied to flow for cases, applied for cases, applied for flow that is hydrodynamically developing. Also, we had these assumptions that these correlations is valid for the thermal interregion when the flow is hydrodynamically developed. But if we have a Prandtl number greater than 5, still we can use these correlations.